Alrighty, boys and ladies, welcome back to another day of Chem 30. So I'm not here in class, obviously. That's why you have a sub, but we gotta keep going, so we're gonna keep rolling. So last class we talked about how to calculate your hydronium ion concentration. Just kidding, other way around. We talked about how to calculate your Ka from your hydronium ion concentration. Now we're gonna do the opposite. So now your formula is basically still the same, but let's kind of see what it says. So it says before the pH can be calculated, the hydronium concentration has to be found. All right, so if you have the concentration of the acid, the initial, all right, and the Ka value, but not the concentration of the A minus, which is the conjugate base, all right, you can assume that the hydronium ion concentration is equal to the concentration of the conjugate base because they're in a 1-to-1 ratio. So again, you have the formula of, oopsies, Ka being x squared over Ha minus x. So let's take a look at an example here. So they want us to calculate the pH of a 0.250 mole per liter acetic acid solution. So the first step, we kind of start with your balanced chemical reaction equation with your double arrows, of course. All right. So now the thing is, this is a weak acid, right? So when you have a weak acid, this is why we got to use this method. If it's a strong acid, you can just directly do negative log. But anyhow, so let us begin. So now your water is all canceled, right? Because water, you don't have concentrations. Now, what we know is that for your CH3COO, the initial concentration is 0.250. So we have 0.250. All right. Whereas for these, in the beginning, you have 0. That means as we kind of keep going, plus x, this one here, minus x, giving you a total of 0.250 minus x, and then here x, and here x. So this is note, to find the equilibrium concentration, we must determine what x is equal to. Now, the next thing we're going to do is we're going to find the Ka value for your acetic acid. And to do that, we're going to make use of our data booklet. Here we go. Data booklet. I do not have one open, sadly, so let's go open it up. So it should be on page 8-9. Now, I'm sorry, I can't flip this, so my number is going to be flipped on your screen. But if we look for acetic acid, oh, there we go, found it. So we see that it is right over here, acetic acid. So the Ka value for it is 1.8 times 10 to the negative 5. That's what we're going to use. Here we go. Oh, oopsies. So 1.8 times 10 to the negative 5. Alrighty. So now what we're going to do is we're going to use the equilibrium law to kind of fill out our kind of like equation, because what we do is we have products over reactants, right? So what that means is your Ka, so 1.8 times 10 to the negative 5 is going to be equal to your what? This times that divided by that. AKA x times x over 0.25 minus x. Now, if you kind of take a look, what we have is x times x. And when you have x times x, we can just rewrite that as x squared. So now what we can do is, why don't we kind of rearrange this so that it's kind of like in like a standard form of a quadratic equation. So what we're going to do is our first step is we have x at the bottom. So I'm going to bring that up top. Boom, boom. All right. So that's going to give me 1.8 times 10 to the negative 5 times 0.25 minus x, which is equal to your x squared. Using my distributive property, calculator time, here we go. We get about 4.5 times 10 to the negative 6 minus 1.8 times 10 to the negative 5. Ooh, I hope y'all can tell the difference between my x's and my multiplications. So let's make it small x, small times. And then this is x, which is equal to x squared. Meaning if we want to get it into like the x squared plus bx plus c case, what we can do is we move everything over to the other side, and that gives you y equals x squared plus 1.8 times 10 to the negative 5 x and minus 4.5 times 10 to the negative 6. So what that means is your a value is 1, your b is 1.8 times 10 to the negative 5, and your c is negative 4.5 times 10 to the negative 6. And I guess it shouldn't be a y. This should really be 0. All right, so what we can now do is, honestly, you can just plug this into your calculator. So you can graph it and find the x-intercepts. You can get 2 of them, pretty sure. Or you can use the quadratic formula, which says it's negative b plus or minus the square root of b squared minus 4ac divided by 2a. Now, I won't show that because that's going to be a lot of work, but if you want to, you can. So maybe if we can stop the video right now, we can pause it so that the students can try to figure out what your x's are. And once everyone's done, we can continue. All right, so now the x values we get, we have one or two options. We have 0.002112334, and the other one we had was negative 0.0021334. So now remember that x represents the concentration of your hydronium and your acetate ion. So if we think about it as a concentration, can we really have a negative number? No, we can't. It has to be positive. So what that means is we reject this guy, meaning this is going to be our x. And I should put in my units. So mole per liter. So then, to solve for pH, we're going to take the negative log of this number, 0.002112334. All right, and that will give us a pH of, with sig digs, let's take a look at our sig digs real quick. 1, 2, 3 sig digs. Right? So that means we want 2.675. And that will be our final answer. All right, so again, feel free to pause at any time if people have to catch up writing. All right, next example. Now, obviously, having to graph it, I mean, graphing it is pretty easy, but like using the quadratic equation is pretty hectic, especially when your numbers are super, super, super tiny. So we have a little trick where we can kind of ignore it. All right. So avoiding the quadratic equation. So the assumption for Ka. So it says if the initial concentration of the acid HA is at least 1,000 times its Ka value, then you may assume the initial and the equilibrium acid amount concentrations are equal, because they're so, like, the difference is going to be so small that it won't even matter. That means that when you have your HA minus X, it is the same as your HA, because again, this number is so small that it doesn't matter if it is 1,000 times the HA compared to the Ka. All right. So instead of writing it as X squared over HA minus X, we just write it as X squared over your HA, where X is equal to your hydronium. That means if I want to solve for my hydronium concentration, you know what? Let's solve for it real quick. What we have is we have Ka equals X squared over HA. So if I want to solve for my X, first thing I want to do is move the HA over. So that gives me HA times Ka is equal to my X squared. Then next step is I square root both sides. I hope we can see yellow. Square root both sides. So that means your X is equal to the square root of HA times Ka. Now, again, we're not going to take the negative version of it. So usually when you square root, you have the positive and the negative, but we're not going to take the negative version of it because you can't have a negative concentration. All right. So example here says, calculate the pH of a 0.250 mole per liter acetic acid solution. So here we go. The first thing we're going to do is we don't want to graph it out, and we don't want to use a quadratic equation. So what we're going to do is we're going to first start with the assumption check. So in tests, make sure you always do this. All right. If you don't, then I'll dock you mark. Please and thank you. So the assumption check is we want to make sure that when we take our HA and we divide it by our Ka, it should be greater than 1,000. So the Ka for acetic acid from above, we said was what? 1.8 times 10 to the negative 5. All right. So we had 0.250 divided by 1.8 times 10 to the negative 5. So when putting it into your calculator, make sure you put brackets, eh? So if this is true, that's good for us. If it's not true, then that's not good. So here we go. 0.25 divided by 1.8 times 10 to the power of negative 5 ends up giving us 13888. All right, so it holds. So since 13888 is bigger than 1,000, that means we can straight up use this formula right here. All right, so that means the hydronium ion concentration, you know what, I'll write out all my steps, is equal to the square root of your Ka times the HA, which is the square root of 1.8 times 10 to the negative 5 times the initial acid concentration, 0.250. 0.250. All right, so that gives us what? Let's square root that. So it gives me about 2.12. So I got like 2.121 times 10 to the negative 3 mole per liter. Then lastly, to find my pH, I take the negative log of that number. So 2.121, yada, yada, yada. And I get about, again, 3 sig digs, right? Yep. So 3 sig digs, 1, 2, 3. 2.673. So if we look at the answer from above, so over here, we had 2.673. If we look at the question from above, 2.675. So the answers are pretty close, right? But again, it's going to be a teeny weeny bit off because of the assumption check, right? And that's all right. So in most cases, especially in diploma, this is the method you're going to use, all right? So just make sure you do the assumption check. But they should all really pass. They'll always pass. But on test, make sure you do it. All right, okay. So now, example number 2. It says predict the hydronium ion concentration, the pH, and the pOH for a 0.200 mole per liter solution of methanoic acid, and the Ka for methanoic acid is 1.8 times 10 to the negative 4. So you see how this question is basically pretty similar to the one on your quiz and unit test, where it's asking you for 3 different things. So all these 3 different things, you have to make sure you get the correct number of sig digs and you label it out. I'll tell you what that means soon. Or I'll show you, I guess. So here we go. In order to find the H3O, the pH, and the pOH, well, we're first going to do our assumption check. So for your assumption check. So what we're going to do is, again, we want, when we divide it by our HA, and we divide it by our Ka, we want to see that it is bigger than 1,000. So here we go. So the initial concentration of the acid was 0.2. So we have 0.2. Then your Ka is 1.8 times 10 to the negative 4. So let's see if that passes the test. 0.2 divided by 1.8 times 10 to the power of negative 4. All right, we get about 111. Or no, not 111, 1,011, 1111.1. All right, so that is indeed bigger than 1,000. So our assumption check is complete. So that means we can now go ahead and just say your hydronium concentration then is equal to the square root of your Ka times Ha, which is the square root of 0.2, well, hold on, pause. 1.8 times 10 to the negative 4 and 0.2. So when I do that, what do I get? Let's see. Oh, sorry, dropped my pen. All right, so now we want 3 sig digs. We're just kidding. We don't want 3 sig digs. We want 2 sig digs. 1, 2. So that means for this part, 6.0 times 10 to the negative 3 mole per liter. So I'm going to square this because this is one of my answers. And I have to get it in the right number of sig digs. All right. So we take care of the H3O. Now the next thing they want is the pH. Well, we're running out of space here, but we'll try to do it here. So for the pH, that's the negative log, right? So that's the negative log of your 6.0 times 10 to the power of negative 3. So if I were to put that in my calculator, negative log. All right. Now, again, we want 3 sig digs. No, just getting 2 sig digs, 2 sig digs. That's going to be 2.22. All right, I squared this answer. That's my pH. All right, then the last thing it's asking for is our pOH, and we can find that. All right, so pH. So to find the pOH, we take 14 minus, right? So maybe we'll do it here. So to find pOH, now this is where you watch out. This is where you keep using the unrounded number. Okay, so you do 14 minus 2.2218 dot dot dot, and that you have in the calculator. 14 minus that, and you get about 11.7. It's 778, so it'll be 78. All right, boom. Third answer. All right, so notice how every single one of my answers for my H3O, oopsies, my pOH and my pH, I have it all like clearly labeled circles. Well, not really a circle, it's a rectangle. So rectangle, 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 and they're all in the correct number of sig digs. So that's what you want to do for the test. Because I'll tell you right now, there will be a written response question that's worth about 4 marks, I would say, where it's asking you for multiple things. Right? So first thing, assumption check. All right, then you do your formula. You get the H3O, boom. All right, then you negative log, get pH, boom. Then to get the pOH, 14 minus, boom. All right, so again, for strong acids and weak acids, there's difference. If you have a strong acid, the hydronium ion concentration will be equal to the initial acid concentration. So now, for your weak acids, if you take your HA and you divide it by your Ka and it is less than 1,000, you got to use the quadratic equation. All right. So usually you won't need to solve this. Usually, I'll still make you solve it, but you know they usually won't happen. But if your HA is above your Ka, sorry, when your HA divided by your Ka is bigger than 1,000, then we can use your Ka is x squared divided by your HA, or you can say the hydronium ion concentration is the square root of your Ka times the concentration of your initial acid. All right, so we got 3 more examples. Here we go. Example number 3. It says, a northern lake has been exposed to large amounts of acid rain. Assuming that the lake water is usually dilute sulfurous acid. Sulfurous, what am I saying? Sulfurous. That has a concentration of 0.010 mole per liter. What is the pH? So first thing we're going to do, if this is a weak acid, start with the assumption check. Assumption check. All right, so again, we're going to take the HA, 0.01. I'm going to divide it by the Ka of sulfurous acid. Let's go find sulfurous acid real quick. Here we go. Back on the data booklets. We are now playing the game of who has the best eyes. Oh, I see it. Sulfurous acid right here. All right, so if I keep going, I see that the Ka is 1.4 times 10 to the negative 2. 1.4 times 10 to the negative 2. All right, so let's divide them and see. Oh, again, we want to see that it is bigger than 1,000. Let's do that real quick. 0.01 divided by 1.4 times 10 to the power of negative 2. Boom. Uh-oh. We got a problemo. 0.71. All right. Now, I don't know what world you live in, but in no world is 0.71 bigger than 1,000. So in this case, you would have to use either graphing or you use the quadratic formula. So now, so this one you don't actually have to do, but we'll just do it just for the fun of it. So they want to find the pH. So again, to find the hydronium ion concentration, right, we have Ka is equal to x squared over your HA minus x. All right. So now your Ka was, okay. So we have, so that's actually 0.014. So 0.014 is equal to your x squared. Oh, and I put square brackets wrongly. This should be minus x like that. x squared minus 0.01 minus x. All right, so we start by bringing this up there, which give us 0.014, and then 0.01 minus x is equal to x squared. All right, we're going to distribute, bow, 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 bow. So that gives you, hold on, 0.014 times 0.0, oh, Jesus. So that is 0.000, hold on, 1, 2, 3, 4, yeah. 14 minus 0.014, x is equal to x squared. Moving it all to one side, we get 0 is equal to x squared plus 0.014x, and a minus 0.3 zeros. 0.301. Oh, Jesus. Hold on. Oh, my days. One four. All right, cool. So now that means your A is 1, B is 0.014, and C is negative 0.00014. So again, use your calculator, or you can do the quadratic equation. So I'm going to just quickly punch this in my calculator and just kind of see what we get, okay? So in the meantime, y'all try to do that as well. All right, I got it. So the x's can either be 0.00, oh my days, 6747, yada, yada, yada. Or it can be negative 0.0207477. So obviously we're not going to take the negative one. So this is going to be our answer. All right, so what that means is we're going to take the negative log to find the pH. We're going to take the negative log of the 0.006747 ... which gives you a final answer of, hold on. So I get about 2.17. And now, how many sig digs do we have? We got 2 sig digs. So 2.17. So 2.17. Now, I'll tell you right now, like the ones, yeah, usually you won't have to do all this, but you know, just always make sure you do the assumption check. Please and thank you. All right. So now, example number 4 says, what is the pH of a lake that contains 1.14 times 10 to the power negative 5 molar of nitric acid? First thing we're going to do is look up nitric acid. Is that a strong acid or a weak? And I'm pretty sure it is a strong. Yes. So nitric acid is a strong acid. So we don't have to do all that like Ka, yada, 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 boom, boom, pow. We don't. All right, you can't even do it because if you want to find the Ka or want to use the Ka, it just says very large. So it's like you can't even do anything. So that means, again, when you have a strong acid, the H3O plus concentration is equal to the initial acid concentration. So that means if I want to find the pH, all I got to do is just take the negative log of 1.14 times 10 to the negative 5, which is going to give us what? Negative log 1.14 times 10 to the power of -5. So we get about, oh, that's interesting. 4 point, we want 3 sig digs, 1, 2, 3, so 3 decimals. 4.943 as our answer. All right. So not too bad. Pretty light. Now, last one. Did I just scroll up by accident? Oh, my days. I'm sorry. Last one. Example number 5. We have, what is the pH of a lake that contains 0.014 mole per liter of boric acid? Now, it gives us that the Ka of boric acid is 5.8 times 10 to the -10. All right. So let's do that real quick. So first step, always the assumption check. Here we go. 0.014 divided by 5.8 times 10 to the -10. We want to make sure it is bigger than 1,000. All right, now, I can tell it's bigger than 1,000, but let's just kind of check. 0.0 divided by 5.8 times 10 to the power of -10. Whoa, hold on. I punched it in wrong, guys. Hold on. All right, so we get about, oh, it's a big number, but it's like 2413791. So that is definitely bigger than 1,000. So we're good to keep going, keep rolling. All right, so what that means is, in order to find my H3O plus concentration, I take the square root of my Ka, 5.8 times 10 to the -10, times the concentration of my HA, 0.014. All right, that gives me, hold on, about 2.849 yada 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 times 10 to the power of -6. So then, to find the pH, and I guess you can put mole per liter there if you want, doesn't really matter. You take the negative log of the concentration, so 2.849 yada 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 times 10 to the -6. So we get, without rounding, is 5.545221985. All right. So with rounding, or sig digs, we see here we have 2 sig digs. Here we have 2 sig digs. So we want 2 sig digs, aka 2 after decimal. So 5.55 for your final answer. Alrighty? And I guess if you want to just do a bonus question, here's bonus. I would like you to find the pOH of the solution and also the hydroxide ion concentration. Alright, so if you do it correctly, the answers you should get with correct number of sig digs should be 8.45 and 3.5. Whoa, sig digs. 3.5 times 10 to the -9 mole per liter. All right. So try to get those 2 answers. All right. But with that being said, the lecture portion is now complete. Now the sub will direct you towards questions on the CYU that we should all be working on to help us better practice. Thank you and have a good rest of your Friday, and I hope you have a good weekend, because I know I will.
Bye.